Recording in progress. Yeah, can you see my screen?
Yes.
And only screen, right? Okay, so this third group study by Group 8 covers the two papers, comparative analysis of search algorithms and severe weather avoidance using informed heuristic search. So what we have learned from the two papers are two different AI search algorithms. So one is uninformed and the other is informed search algorithm. Uninformed algorithm blindly explores every path until it reaches its goal. So it's like visit all the nodes. And it's similar to brute force because both does not use more effective way to reach the goal node. On the other hand, uninformed algorithm searches an optimal path by estimating the shortest cost between the current node and the goal node. This job is done by heuristic function, which helps to choose more promising nodes and makes a significant difference from uninformed search algorithms. So the first research paper, Comparative Analysis of Search Algorithms, provides brief explanation about some informed and informed search algorithms. The third research paper, Severe Weather Avoidance Using Informed Heuristic Search, presents the application of an informed algorithm to free flight. So this presentation consists of 3 parts, and each of us discusses what we have learned from the 2 papers in more detail. Che presents the first paper, the idea of search algorithms and comparison of them. Yoni, me, explains how A star search, one of informed search algorithms, is utilized in free flight. And lastly, Siri provides how their searching algorithm works in real sample cases and conclusions. Jay, can you share your screen?
Yeah, thank you. Can you see my screen, right? Yeah, okay. Today I'm going to discuss about comparative analysis of search algorithm. In this paper, we have mainly discussed on what is such algorithms working and an in-depth evaluation of information and uninformed looking methods in the presented in the paper. A-star and the best first search are the examples of educated look methodologies. The paper more heavily emphasized ignorant look methodologies like BFS, DFS, and UCS. In addition, the paper shows how to work with looking techniques, the merits and the demerits, as well as an open list and a closed list for each conclusion. Towards the end of the analysis and tabular representations of look strategies based on their complexity, optimality, and completeness are displayed. And in search algorithm, we have 2 approaches: uninformed search and informed search. Uninformed search, it is made up of blind or blunt force search strategies like breadth first search and depth first search, and uninformed cost search. It would depend on and bidirectional searches. There is no information provided during uninformed search about how many steps are required to achieve a goal state. Rather than considering the most effective and optimal path of a goal, Uninformed search consider the path that appears to be the most promising at the time. So informed search is a heuristic search method that solves a problem by utilizing functions that generate, and the test methodology is used for informed search. And we we can use the heuristic search to help guide us to the desired result. It is not going to be a random search. It will evaluate some evaluation functions from the current state to determine the next node to transfer to reach the goal state. And here we can see the working of how the search techniques all in what in BFS, breadth first search, and depth first search, and UCS, A star, and A star is going to explain about this part is taken to here, and best first search, greedy search. BFS is an algorithm used to discover or find a data structure such as trees and graphs before proceeding to the next node. At a deeper level, the current depth level is explored. And DFS is used to find data structure in a graph or trees. Starting the root node of the tree, the algorithm descends as far as it can give via branch, and the backtrack until it come across an unexplored branch, which it then explore. The repeat by the algorithm until the entire graph is explored. UCS is an ignorant look calculations that uses as the smallest total taken a toll to find a path from the source to the goal. Hubs are extended from the root with at least amount of aggregate taken into account. The priority queue is used to implement uninformed cost loop. A star. A star algorithm is a search calculated the shortest path between the starting point and the end point. It is used a variety of applications, including mapping. Best first search, it's greedy search, is a combination of breadth first search and depth first search. The priority queue is used to implement the best first search. And here we have discussed the first search method. It's breadth first search, and here's some applications and graphs. So table of I explain how the graph represents. I'll explain all in detail. All nodes are explained by level in the breadth first search. It explains all of the nodes on the first level of the search tree, then all the nodes on the second level, and so on until it reaches the goal. BFS is a queue that works as a first in, first out. It means when the queue starts, which comes first, and it goes first out. The table shows some two and one open list and the closed list. So here I am explaining how the open list numbering and all the things. And in the level 1, and we have 3 child nodes, as we just entered into the 2, 3, 4 in the queue. We added into the queue, and here and the next we have the closed stage, right? So it will take the first in, first out. So we entered in the open list 2, 3, 4. So the here the first out is 2. It shows in the closed list, and we have the at position number 2, and here we have the child 4 and 3 and 6 we have. So 3 already we have. So 4 and 1 6 is added to the queue. So, and next the node position we just check up, and next node changes to 3, and because in the open list we have 3, 4, 6. So it changes to first out 3 and checking the child nodes which are connected to the 3. So here we have the 4, 5 and 2. We have already traveled to 2 to 3. So we have a new node is here 5. So we just added it into the 5. So like this, we the nodes travel and until how the search get to goal state. Here we have some applications applicable when the memory is not in use as an issue here. You must find the solution to find the problems with the fewest curves. Few solutions may exist and at least one has a shortest path. And here some advantages and disadvantages. The shortest path between the starting point and other reachable node is found by BFS. And deep depth first search does not have always yield the shortest path. In general, BFS require more memory than BFS. And next, depth first search. Depth first search is expand source node that the deepest unexpanded node is a stack, works as a last in first out. So the table, as usual, the table shows open list and close list. And here I am explaining some of the how the nodes travel from to reach the goal state. Here we have the same concept, but here we are using stack first last in first out. So it's the same thing. One has two 3 childs. We entered 4, 3, 2. So here we have the last in is 2. So it added 2 into the, let's go out. So 2 is out. So next we are at the position at the 2. Here we have 3 and 6. So already we have the 4 in the stack and 3 in the stack. So we added a 6 into the stack. So and the position is 6 is out. So the position we are at 6. So 6 doesn't have any child here. So it transferred to the position. Sorry. So it transferred to the position 3 and it checked the 3 how many childs they have. So 3 is out. So we are at the position in 3. We have 2, 4 and 3. We have 4 in the stack. 2 we travel from the through 2 to 3 here, and the 5 is added to the stack. Like this we travel to the goal state. And here's some applicable when memory is limited and the order in which we nodes neighbors are added to the stack and can be turned to find the solution on the first try. It is a poor technique when it is possible to capture in the infinity number of ways, which occurs when the graph is infinity or when there are cycles in the graph. So here's some advantages and disadvantages. In general, depth first search on a binary tree uses less memory than breadth first search. Recursion makes it simple to implement depth first search. And disadvantages, DFS will not always find the shortest path to the node, whereas breadth first search. And UCS, uninformed cost search, and the node is finding the cheapest path, and the priority queue is used to implement considering the equation calculated the cost of each node. And is when it's previously node, and here the key equation C of M is equal to C of N plus C of N and M. So here C of M is the current nodes of cost, and the C of N is the previous node's cost. C of N comma M is the edge weight. So those who are already in the queue at higher cost then can be removed as a success. So CSS is applicable when a space requirement is less, when intelligence is not required or the evaluation function is not required. So some of the applications we have, you are using the solving math problems and pathfinding. So we're using some techniques here. And the best first search is a greedy search. As I mentioned in the before, the breadth first search is combination of BFS and DFS implementing, and it provides solution without having the calculation every node, while breadth first search finds a solution without searching the preceding the guarantee or not to be caught. Breadth first best first search, which is a hybrid of two, allow license to switch between the paths at each stage. The best appropriate node from among the create ones is chosen, facilitate expansion. This node may have the place on the similar level or different level, and thus can switch between depth first and breadth first search. It also it also refers to as a greedy search. The time complexity and the space complexity is checked. So here is some applications we are using the games and web calling. So finally, here we are comparing various search algorithms based on algorithms. We have time complexity, space complexity, or optimality, and completeness. So what is what is time complexity? Complexity, the amount of time is taken the algorithm to find a solution. And space complexity, the algorithm requires memory to perform the searches. Optimality, the algorithm will always provide the best solution whether it is optimal or not. Completeness, in that calculation guarantee to yield an answer when it says it does, regardless of whether the search algorithm is thought or not. This section is a Boolean marker. So here we have mentioned some equations what we are using: BFS, DFS, and UCS, and A star and BFS algorithms. So this is my part, and I just hand it to in to explain you. Thank you.
Okay, thank you. Okay, now I'm going to introduce the second paper, which names Severe Weather Avoidance Using Informed Heuristic Search. This paper suggests thunder avoidance algorithm that aims at computing safest and shortest flight path in the presence of thunderstorm. In the radar image depicted by 2D Gaussian function, this yellow and red zone represent high intensity that must be avoided. Hence, a question comes to our mind: how will a flight reach the endpoint? So the endpoint is this one, this flag. How will a flight reach the endpoint without passing this dangerous zone? The paper adopts A-star search for the thunderstorm avoidance algorithm. The function for A-star search is Fn equals Gn plus H of n, where G means actual cost between the current node and between the current node and the next node, and H of n means the estimated cost between the next node to the goal node. A-star search intends to minimize the value of the actual cost f with the help of heuristic function h. The value of g, which is the actual cost, does not change. It is static. Thus, we can reduce the total sum f by choosing the lower value of h. So, for example, we need to choose between A and B to reach the goal node. This is the start node. And the actual cost G from the start node to node B is 3, and the actual cost G from the start node to node A is 5. So for example, A, the actual node is 5, and B, the actual node 3. Choosing node B appears to be more efficient, but in fact, choosing node A is more efficient considering the total cost. So this yellow number is the estimated cost from A to the goal node, which is 2. And the estimated cost H from B to the goal is 8. And the total cost of A will be 7, and the total cost of B will be 11. Thus, choosing A is more efficient because the total cost is much smaller than the total cost of B. So this is the general concept of A-star search. However, this algorithm fully takes the memory because it stores all the nodes in the memory. So this is the problem. So this paper solves the memory inefficient problem by modifying A-star search. Before applying the algorithm, a few stages is needed to take. First, divide the map into grids to set accessible and inaccessible region. Not only the grids in the map could be bigger than that in the radar image, but the radar images cannot always be accurate due to uncertainty in the measurement. Considering the two facts, set a grid in the map to maximum intensity and set areas in the intensity larger than 25 dBz to inaccessible zone. So what I mean by that is, just imagine that this one is a map, and each box represents a grid. And as you can see, the grid in the map is much bigger than the grid in the radar image. And like, for example, this red box will contain red, yellow, green, and blue, like the 4 colors, right? And this box will be colored as red because red represents the most intensity value. Then next, draw lines. The number of lines are decided by minimum segment length and minimum number of turns. So what I mean by segment line is, segment line means the distance of these 2 points in the map. I don't know the specific about aerospace theories, but according to the paper, it says the number of lines are decided by minimum segment length and minimum number of turns, which means that the lines are drawn like this. If this is the starting point and this is end point, and this flag is inaccessible region, like dangerous region. Third, choose nodes on the lines. And the number of nodes is static, so any path is chosen will have the same number of nodes. So the nodes on the line here like this, and it will choose the node, the most effective path like this. And note that nodes between this point 1 and 2 should be avoided because I think this area is too close to the dangerous zone, to the thunderstorm. So it is dangerous to choose the nodes between point 1 and 2. And lastly, finally apply A-star search algorithm. with a heuristic function to search the safest and shortest distance. After that, the strategies for efficient use of memory are used in thunder avoidance algorithm. First, remove a node with the highest cost f from the memory if the system has no memory left. Next, the algorithm does not keep the best forgotten path. The best forgotten path is retained in the memory to prevent duplication of the same nodes. But no same nodes lie at the two different lines according to their algorithm. So it was difficult for me to understand this part, but I think the paper is saying that if this is the line and the nodes on the different lines are different, so they are not the same. In addition to that, allocate the right size of memory so that the one required for the best path can be properly stored. The optimal path sometimes does not run on the system if it has a limited size of memory. To prevent this memory issue, the size of memory is allocated after the optimal path is computed. So like for example, if the optimal path required 5 GB, but the memory we have is like 2 GB, then it will be impossible to run this optimal path in our system. So it suggests the size of memory is allocated after the optimal path is computed. Okay, so my part is over here, and Siri will continue the next part.
Okay, I'm going to continue the this paper and this result. So hi guys. So the result of this A-star search is the paper gives us several cases to prove how successfully thunderstorms avoidance algorithms run on the real situations. Yoni is really explained good way. So now I'm going to tell in the real world scenario. So what is the thing is, if we have a one flight, when we are traveling in a flight mode, if a flight is already in the thunderstorm zone, the algorithm cannot give a safest path. This is because of the algorithm does not allow the turning back changes. So algorithm is not suitable for the long area of map, because as mentioned earlier, the algorithm generates the optimal path, gives the minimum segment length and the number of turns. So this is the disadvantage of this thing. And what is the how do we implement this thing is readjust the limit of incredible reasons, like just minimum distance, it should be fine. To make it more enhanced algorithm, readjust limited like 250 dBz to 20 dBz, it's good. There is a minimum distance between the inaccessible region and nodes close to the region to separate them. In addition, the ability of the flexibility to adjust the minimum segment length and the number of the turns according to the size of the direction of the thunderstorms to be then needed. So finally, the conclusion of the part is first. Okay. The conclusion of the part is to show the algorithm calculate the safest and shortest path in the small area of the map is correctly. So in the AI search technique has been modified to ensure the answer is from the short period of the time. So this technique is applied to 5 different thunderstorms like scenarios, and the simulation results for the moving thunderstorms are provided. In this research, a severe weather avoidance algorithm for the general aviation is created. So the algorithm is based on the AI search principle with appropriate modifications based on SMA star search techniques to reduce the time and space requirements. The problem is modeling to ensure that assuming the underlying assumptions are correct, the algorithm will generate the safe flight path in a short amount of time. This is the conclusion of this part, second paper. So thank you guys.
Thank you.
Yeah, thank you. You please stop. Okay, good, thank you.
Sorry.